So as we approach this proof, let's take a gander at our situation. So down here, we have a right triangle who has, here's my A, here's my B, and here's my hypotenuse. Now what we've done is effectively just copied and pasted after we rotated. So that means this one here is my B, because it's the shorter side right there. So my shorter side. So that means my B is up here as well, and up here is my B. Now continuing, my long leg is my A, so there's A, and A, and A. And I will put my right angles everywhere. And clearly here, my hypotenuse is C, so all of these are C. So we have copied, pasted, and rotated all the way around to create one big shape. One big shape. So this large shape is a square. We know that because this side down here is A plus B. And this side over here is A plus B. So we now have a large square. On top of that, we have 5 smaller shapes. We have 4 congruent triangles, and we have a twisted square, that C squared there. All right, so what we're going to do is treat this as an area problem. We are going to find the area of the large square, and then we're going to find the area of the parts. And what we're going to see is they should be equal. So here is my setup. I'm going to say the area of my square is going to equal to the sum of the parts. And of course, we've got 5 components. And here there are, I'll go ahead and put that in, the sum of the 5 parts. They should be exactly the same, like a puzzle piece. All right, so let's see. The area of my square, remember, is base times height. So the area, my length, or my width here is A, so A plus B right here, and also A plus B right there. So I'm going to write that twice. Base times height, A plus B times A plus B. Now notice I have 4 right triangles, and the way we consider right triangles is 1/2 base times height. So if this is my base and that's my height, I have 4 of them, and I'm going to multiply that by, so I have 4 triangles, and each triangle is 1/2 my base times my height. So they're all congruent, so they each have the same area. And the last figure to consider is that black square. So the area of that square is simply C times C. Or another way to write that is C squared. So here is the situation thus far. The 2 areas should be exactly the same. Now, applying our super secret rule over here for double distribution property, I'll go ahead and multiply this out to be A squared. And this one here is AB, and that should be a plus in between. And now multiply this out to be AB, and multiply this out to be B squared. Now I can simplify here. 4 times 1/2, or 1/2 of 4 is simply 2. So now this simplifies to 2AB plus C squared. Now on the left side here, I'm going to combine like terms. The middle 2 terms are like. This is 1AB, this is 1AB. So in total, I have 2 ABs. So A squared plus 2AB. So again, these 2 combined to get that bring down a B squared. Now on this side, I have a 2AB plus a C squared. Now what do you notice on both sides? Say it again. Now I have 2AB here, so I'm going to subtract it. And whatever I do to one side, I do to the other. Negative 2AB here. So these drop out to get 0, these drop out to get 0, and I'm left with a squared plus b squared equals c squared, which is the Pythagorean theorem. So in this application, we have metal expands and contracts, gets smaller, with changes in temperature. The transatlantic pipeline was built to accommodate expansion and contraction. Suppose it had not been built this way. Consider a 600-foot section of pipe that expands 2 inches and buckles as shown. So let's go ahead and take a moment to draw it out. So we have a pipeline that is 600 feet. So here's my pipe. All right, so this is 600 feet long. So this says it buckles only 2, or not the buckling is 2 inches, but that it expands 2 inches. So let's go ahead, and now we're going to put the pipe up a little bit. So it is now kind of broken like this. Okay? And it should be more in the center, so we'll ignore that. So this now is 300 feet here, but remember it expanded 2 inches. So that means it expanded 1 inch on this side, and 300 feet and 1 inch on this side. So now it's asking us to estimate the height of the buckle. How high is this right here? How high is this right here? So now what we have is a right triangle, and we're only going to consider one of these right triangles right here. So down below here is 300 feet, and this one's 300 feet and 1 inch. We're going to convert that to a decimal in a second, and we're going to try to find h. Now, h is not my c. So first off, let's convert the 300 feet and 1 inch to decimal. Remember that 300 feet and 1 inch is 1/12. So using a calculator, we can just punch in 1/12 in a calculator, and we get 0.083, and of course that does repeat forever. So I'm going to keep that in my calculator. I'm not going to write the whole thing down. Just keep that in my calculator. Now, we have Pythagorean theorem, which says a squared plus b squared equals c squared. And according to my diagram, my c is right here, my hypotenuse. So I'm going to put the 300.083 right here. And the other side of the triangle is the leg on the bottom, so that's 300 feet here. We don't know what b is, b being my height, so let me actually change that to h for height, not h for hypotenuse. And I forgot to square the 300. And this equals my c, which is 300.083 with a square on it. The calculator comes in very handy. 300 squared is 9 with 4 zeros, 90,000. I don't know what h is yet. Now when we evaluate these, 300 squared is 90,000. 8 squared comes down. This is an approximate, so I change the symbol. And this square becomes 90,000, 50.0694 approximately. Subtract 90,000 from both sides to get approximately 50 over there. Now all we have to do is hit the square root button right here and here. Now mathematically we get a negative answer as well, but we don't need to consider that. And when we take the square root, we get 7.07 feet. So 2 inches of buckling, 2 inches of growth here will break the pipe and shove it up 6 or 7 feet right here. And that's just 2 inches. And that's just 600 feet. What if it were 6 miles and it buckled just a few inches? This could shoot up high. Now, of course, what's going to really happen in a situation like that is that it won't just buckle like that. Rather, it's going to buckle all over the place. So you're going to have many, many breaks. And of course, that pipeline would be demolished. In this problem, we're asked to find the diagonal of the screen. So from one corner to the opposite corner like that. So we're finding the diagonal, which is how TVs are measured. I have a 55-inch television. I have a 10-inch television. I have the Samsung 105-inch UHD. So all we have to do is pretty much effectively set up a right triangle right here. So we have a 38 and a 44 for my legs, and I'm trying to find the hypotenuse. So now we set it up. A squared plus B squared equals C squared. So one of the legs, remember it doesn't matter which one is which. It doesn't matter which one is which as long as you're consistent with the hypotenuse. 38 squared. And lastly is my unknown C. You could call it whatever. We'll keep C here. And now to simplify here, we get 1936 plus 1444, all equals my unknown diagonal. Now I'm going to combine like terms, or just combine those constants, to get 3380. And then we have to just take the square root from both sides, the square root of both sides. Mathematically, we get a negative number as well, but we can ignore that. And after we simplify, we take the square root, we see we have a 58-inch television.